we'll start recording. And yeah, let's start with question 1. Oh, I already.
Someone check to make sure my.
Yeah, it's proper.
It's good?
Yeah.
Okay, sounds good. So, question 1 is where we start with chapter 13. Yep, this is chapter 13, question 1. So, in introductory physics laboratories, let me open up my notes. Laboratories. Here it is. So, a typical Cavendish balance for measuring the gravitational constant G uses lead spheres with masses of 1.5 kilograms and 15 grams, whose centers are separated by about 0.45 centimeters. Calculate the gravitational force between the two spheres, treating each as a particle located at the sphere center. Okay, this is easy. We just use this formula. What are we looking for? The gravitational force between the two spheres. So we just use this one formula. That's it. So the gravitational force is, the magnitude of it is G, M1, which is 1.5, M2, which is 0.015, over R squared, which is 0.045 squared. Yeah, and there you go. So that should be it. Let's just make sure that's right, and then we can move on. G is 6.67 to the 11. I mean, times 10. Is it times 10 to the 11 or times 10 to the negative 11?
Negative 11.
Negative.
Negative 11.
Thank you.
I think the one that's positive is the electricity one.
Oh, I see.
Positive 9.
Answer divided by 0.045 squared. So I got that the force is 7.41 repeating times 10 to the negative 10. And may as well check newtons. May as well check the answer.
It's correct. I have it right.
Okay, sounds good. Thank you. Next one is number 2. So number 2 is here. During a solar eclipse, the moon, the earth, and the sun all lie on the same line, with the moon between the earth and the sun. What force is exerted by the sun on the moon? What force is exerted by the earth on the moon? What force is exerted by the sun on the earth? Compare the answers to part A and B. Why doesn't the sun capture the moon away from the earth? So this is essentially just the last question again. We just use that formula. We just have to know this. We just have to know the distances, which we don't know. It doesn't give us all that. So I think I'll just skip the calculation part. We'll get some sort of values, and presumably by the last question, the force from the sun on the moon, is greater than the force of the earth, right? Because if you compare A, sun on the moon, B is earth on the moon. Yeah, earth on the moon.
I
Right.
think to do this question, we
No.
need like all of the masses and the
Yeah, we just need the masses and the distances, which they would give us.
I think you have it on the opposite. The Earth and the Moon will be stronger than the Sun of the Moon. That's why.
Yeah, otherwise
That's
the
why the
moon
sun-
would go towards the sun.
But the question is, why doesn't the sun capture the moon away from the earth? Oh, is it because this
Yeah,
is less?
Yeah.
Yeah.
Oh, okay. I expected by the way that the question was phrased that it would be this, but I guess it's that, and it's that because, because the calculations are like that. That was what we would get, and that's why it doesn't steal the moon away.
Just think of centripetal acceleration. What direction does the force have to be in order for the moon to orbit the Earth?
Yeah,
And not the sun.
that's true.
It has to be pointing.
Has to be
towards
pointing
the Earth.
towards. Yeah, that's true.
Wait, yo, I have a question.
Yeah.
Oh, what does it mean by sun captured the moon away from there?
Like, if the moon is here, Earth is here, sun is here, and the sun is producing this kind of force that way, and the Earth is producing this kind of gravitational force that way. Right, I'll call that one F1, F2. Why doesn't the sun just sort of like, because the moon is right now orbiting the Earth, right? But why doesn't the moon just start orbiting the sun if it has a bigger gravitational field?
Oh, okay.
Well, because it's the force, I guess. The force is greater here, and the direction of the net force is going to be towards the center of the Earth, which causes the centripetal acceleration around like this.
But like realistically, wouldn't you still have some force from the sun, but like
Yeah.
it's very negligible?
Yeah, but since this is, I think the important thing is that the net force is pointing towards the Earth, because,
Wait, yo,
yeah.
Loki just got confused. I understood everything, but that last part I just kind of got confused.
Why don't we
what
get
should
the numbers? Why don't we actually get the numbers, and then we can compare it
Alright,
like
yeah.
that? Yeah.
Yeah.
Let's get the numbers. For that,
think-
yeah.
Sorry. It's just because the R value between Earth and Moon is way much smaller than the one between Moon and Sun.
Yeah.
So the gravitational force will be stronger on the.
Earth and
Yeah.
Moon is that.
Yeah, and also it's just the fact that like it's inverse square, so like if it's squared, then it grows like exponentially. So it's also that.
Yeah. And then this would be the what am I looking for? Mass of Earth, Moon, Sun. So I need all these numbers. I don't know these numbers. Let's see. Wait, we just did a question like this, I think. So I think I can just use that. Let's see. Oh, I'm in the wrong spot. Let me see. Yeah. So I know the Earth, the distance between the Earth and the Moon is 3.84 times 10 to the 8. The mass of the Earth is 5.97 times 10 to the 24. Mass of the Moon is 7.35 times 10 to the 22. And I don't know these other numbers. This is 1.989 times 10 to the 30. And distance. Oh, well, hold on. I don't know these. What do I look up for distance between Moon and Sun? That's not a very constant
Correct.
distance.
Distance between Earth and
Oh, okay. Earth and
minus
Sun.
distance between Earth and Moon is distance between
Yeah,
Sun and Moon.
makes sense. Distance between Earth and Sun is 149 point. Oh, it's giving it to me in words. So hold on. How do I do it in times 10 to the million times 10 to the 6 times 10 to the 9? Yeah, that makes sense. 10 to the 9.
What kind of weird thing is gonna give you a number in words?
It says million kilometers, so I was like, hold on, what do I write? Yeah, just the Google answer. I don't know.
I think it's 1.49 to the times 10 to the 11.
Yeah, 1.49, but I was doing 149. So, but yeah, 1.49 would be to the 11.
Isn't it 150 million kilometers?
Yeah, just this.
Yeah,
just this.
just that.
Just this. Yeah. Meters. This is in meters, right? But yeah, was the last thing in meters?
Yeah.
Yeah, it is. Okay, good. Okay, so now force between the sun and the moon. So force between the sun and the moon, and I'm comparing that to the force between the Earth and the moon. Well, I'm just going to use the formula, right? So it's going to be 6.67 times 10 to the negative 11 times the mass of the sun, which is 1.989 times 10 to the 30 times the mass of the moon, which is 7.35 times 10 to the 22 over the radius squared. So the radius between the sun and the moon, that is going to be between the Earth and the sun minus Earth and the moon. So 1.49 times 10 to the 11 minus 3.84 times 10 to the 8 and square that. So I got that this force is 1.414849 times 10 to the 20. Okay, let's see what Earth and the moon is. So this is going to be 3.84 times 10 to the 8 squared, and then it's going to be I just need to replace the sun mass with Earth mass, and That's the only difference. And then the distance changes too. But yeah, 5.97 times 10 to the 24. So I got a smaller number, 1.98985 times 10 to the 20. So this is true. Opposite of what we said. This is it. So in that case, why doesn't the sun capture the moon away from the earth? Yeah, how do I explain it? The force is greater.
It'll orbit in whatever the direction of the net force is, because that'll cause the centripetal acceleration.
I guess, yeah. Because like, it's not, if it was just like this and they were just still and perfectly like this, then yeah, the moon would go to the sun, right? But the moon is orbiting the earth. What that means is that there's a centripetal acceleration that's happening always to the center there, right? And so that's adding a net force inwards, right? So there's adding another force inwards. So the net force is still towards the earth here. But again, if they were just like still, yeah.
Isn't the centripetal acceleration only due to the gravitational force?
It is.
Yeah, so there is no extra force being added, is it?
No, but it'll orbit in whatever the direction that the net gravitational force on it is.
Well, the net gravitational force is that way.
Yeah,
towards
exactly.
the sun?
At the point of the solar.
Towards the
At
sun.
the point of the solar eclipse, it will be towards the sun.
Are you sure we didn't make like a mistake? Cause like I see no way that
I
it should
think
be bigger.
Well, you see the
I
moon.
think what it is that we have to look at escape velocity. I don't think the moon is moving fast enough to get rid of the Earth. I think that's the point. Even if the sun is pulling stronger than the moon, the simple fact is that the moon's already following the Earth's pattern, like around the sun. So they're both technically trapped by the sun. It's just that the moon's so slow, it won't go away from the Earth.
Sure, saying because it doesn't have a high enough escape velocity, so it's not gonna go start orbiting the sun. That's why.
Yeah, that makes sense. But what would they want us to
if you think about it, because technically the moon is already following an orbit of the sun because it's following the Earth. Yeah. So technically, the sun already has the moon stolen, if you want to say it like that, because it's already orbiting it. It's just that the moon's, I think, is so close to the Earth, is that it's not moving fast enough to have its own orbit, and it just shadows the Earth as it revolves around the Earth too. I think.
I have a question.
Yeah, that's what I found as well from the quick search.
In your distance between, you have the distance between the Earth and the sun, but like which is like close to distance between. Shouldn't it be the distance between the sun and the moon?
Yeah. I didn't write it, but I didn't write it. The distance between the sun and the moon is the distance. So my notation's a little weird here, but hopefully it makes sense. The distance between the sun and the moon is the distance between the Earth and the sun minus, that's an actual minus sign, the distance between the Earth and the moon.
Okay, and then you use that.
That's what I used. Yeah, that's what I used.
Okay.
Yeah.
Wait, what?
The distance between, so like if this is the Earth, the moon, the sun.
Yeah.
This distance, right, which is the distance between the sun and the moon. I'm looking for this distance, right? I'll do it in a different color. This distance, which is the distance between the sun and the moon, is equal to the distance between the Earth and the moon. Sorry, the Earth and the sun, minus this distance, which is the distance between the Earth and the moon.
Alright, dang.
Right? No problem. So we got a bigger number for that. And so so now the question does make sense. Why doesn't the sun capture the moon away from the Earth? I think it's to do with the fact that it has centripetal acceleration. I mean, we have escape speed, I know, but
Does this have something to do with like an ellipse? Because, like, its orbits aren't perfectly circle. Is that what they were trying to get at? I don't know.
a quick search I did, I agree with the other
No,
guy.
but then
He
We
said
can
that
skip this
the
question
actual
regardless. Or we just skip this because it's definitely not showing up on the midterm things like
Not
this.
showing up in the midterm, yeah. But yeah, finish. Someone was saying something there. What was it?
I was saying that it's orbiting the sun, so technically, what the other guy said is true. The moon is orbiting the sun
Yeah.
and the Earth at the same time, and the Earth
Yeah.
is orbiting the sun. So
That might be it then.
Yeah, that's what I was
Yeah.
thinking.
What's the
Yeah.
difference between the like? I don't know how. What the magnitude of the difference between those two numbers is. I don't know if that's enough to like. Because maybe it's not actually as big of a difference if you're thinking about an entire planet. It's a very small difference, maybe. I don't know.
I don't know. I think we should just move on. That's what I think.
I mean, like we already got the main idea out of this question.
We got the
Use
main idea
force
out of the question.
gravity.
Yeah. Question number 3. There we go. Let's move on. Determine the order of magnitude of the gravitational force that you exert on another person 2 meters away. In your solution, state the quantities you measure. Okay, I think this is... Okay, we could try it, but this is also not going to show up on the test, anything like this. Yeah. What do you think? Should we try it, or should we...
Yeah, let's do it.
I think we might as well skip
You
it.
have to choose your own values for this.
You have to choose your own values.
Like,
So like,
it's the same formula.
Yo,
We know
this
it's
is
gonna
this
be
is
like
formula.
insanely
It's about
small.
like 50 kgs.
Okay,
Yeah.
so...
Oh, no,
move on.
it's not the same formula. It's actually a different formula. It's the other G formula.
What are we looking for? Gravitational force? No, this was gravitational force, but
It's
the same formula as
thing, it's the
before.
same thing.
Oh, it is gravitational force. Yeah.
Yeah,
I thought
same
it was,
formula as before.
Yeah. All right. Yeah. So.
Okay,
I don't think we have to do this.
I agree. Let's move on to number 5. Number 5 is this one, with a nice picture. So, okay, can I get it to? Okay, so this planet is can be modeled as a sphere of radius that. So we have our radius here is 242 kilometers, and has a mass of 6.68 times 10 to the 19. Okay, find the free fall acceleration on its surface. Okay, that's just the g. That's just the magnitude of the gravitational field at its surface. I think so, which is just gm over r, or I forget what it is. Let's see.
over r squared.
Yeah, gm over r squared. So we just do that. That's it. We just type that in, I think. So 6.67 times 10 to the negative 11 times 6.68 times 10 to the 19 over 200, what was it? 242 kilometers, so 242,000 meters. So I have that it is, squared. I didn't square the denominator. So I got 0.076 meters per second. Squared. Yep, let's check that answer, but that would be good to see. I have to find number.
Wait, so is this the formula? Does it just calculate G?
I think so. See number 5. Yeah, that's right. This is correct.
Which if you were to use this on the surface of the Earth, would you just get 9.8?
Yeah, you would get 9.8.
Okay, thank you.
You get 9.8. Okay, a cliff on Miranda is 5 kilometers high. It appears whatever, and is whatever. Oh, okay, hold on. I gotta find the rest of the question. So we have a cliff that's 5 kilometers high. If a devotee of extreme sports were to run off horizontally off the top of the cliff at 8.5 meters per second, for what time interval is he in flight? Well, this is just a kinematics question because it's constant motion, so we can try it, I guess. Constant acceleration, I mean. So okay, y is negative 0.076 meters per second squared. Vix is 8.5 meters per second. Viy is 0. Delta y is 5 kilometers. Yeah, 5 kilometers, so 5,000 meters. Now I just need the kinematics equations, which are here somewhere. Yeah. And so we're looking for delta t, right? So delta t is, I can use, I don't need the x. Oh, wait, hold on. Oh, yeah, the x doesn't affect how long we're in the flight for. Yeah, that doesn't affect it. So I can just find, yeah, I can just use this one. Delta y equals v I y t. No, that's probably a harder one to use. I don't know the vf. I think I have to use this. V I y t plus, yeah, plus 1/2 a y t squared. And I know everything here, so I can just say 0 equals negative delta y. And I guess delta y is negative 50. Negative 5,000, I mean. VIY is 0 plus. So VIY is 0. AY is that. Delta y is that. Yep, we're good. So it's just delta y equals 2 delta y equals AY t squared over AY in a square root. I'm doing this a little messy because it's just a kinematics question, but delta y over AY. So 2 negative 5,000 over negative 0.076 in a square root. So square root of 2 times 5,000 over 0.076. I got 362 seconds. And let's see if that's the answer. Yes, that is the answer. I can't round, so it's 363, but yeah. So that was just kinematics. I did that messy, so but if someone wants me to explain, I can explain for sure. But that was just, yeah. This is just a kinematics equation. Don't worry if it's confusing. Okay, I can explain it. Kinematics.
This won't probably be on the test either, so we're chilling.
Well, I don't know. I'd say we are kind of expected to know how to do kinematics. So if they mixed one in, I don't know, possibly. But yeah, that's that. And the next one, how far from the base of the vertical cliff does he strike the icy surface? What will be his vector impact velocity? Should I just skip the rest of these? Because they're
What
just
is vector impact velocity?
Isn't that just final velocity?
It's just just kinematics. After this is just kinematics, which I'm not saying is super easy. I'm just saying it's just the kinematic stuff. So I think we would be okay. But just tell me what you guys think. Should I skip it? Should I?
Wait, so vector impact velocity is just final velocity?
Mm-hmm. With magnitude and direction.
Such a weird way of naming it. Just say final velocity.
So
Yes.
This question is just trying to show you that you can do kinematics with any gravitational force.
Exactly.
G is just G.
You just have to figure out what the what the acceleration due to gravity is on another planet. You just have to figure out what that number is, and then you can do just regular kinematics with that number.
Yo, I think you can just skip this one.
I'm thinking that too. Is that good? If that's not good with
Yeah,
anyone,
skip it.
tell me. And I will
Yeah.
Okay.
Can you go up for like 1 second? I just wanna see
Up here?
something. Yeah. Where did you get the negative 5,000? For the delta y?
Here. The cliff is 5 kilometers high,
Oh, okay.
which is 5,000
sorry.
meters,
Yeah,
but you're going down 5,000 meters, so negative 5,000 meters, right? Yeah. Okay, then I will carry on to this one. So compute the vector gravitational field at point P on the perpendicular bisector of the line joining two objects of equal mass separated by distance 2a, as shown in the explain why physically the field should approach 0, whatever. So first, find the vector gravitational field at point P on the perpendicular bisector of the line. Like, that's the perpendicular bisector, I think, of the line. Oh, okay. It's just using too many words to say point P. It just means point P. Yeah, it just means point P. So I need to find these distances, right? So I'll call this one, I don't know, R1 and R2. So R1 is the square root of R squared plus A squared. And R2 is the square root of, well, is also the same thing. Is R2. So now that we have those distances, well, then the vector gravitational field at point P is going to be, so the gravitational field as a magnitude, we're only talking about magnitude here. No, it can't be. No, I want that as a vector. So, okay. I'm going to have to find the gravitational field caused by this first. So I'll call this number 1 and this one number 2. So the magnitude of the gravitational field caused by number 1 at point P is g, the mass of that one, which is m, over the square of the radius, which is going to be r squared plus a squared. Similarly, the gravitational field caused by mass 2 at point P is g times the mass over the same quantity. Okay, now I need the
I think you can use symmetry here, can't you?
And how?
Because in the y direction they will cancel each other, so you have just 2x. So this cos theta, 2 this cos theta.
Oh yeah, 2 times this cos theta. Okay, I see. Yeah. So the vector. So first of all, the x component is going to be something I had. The y component is going to be 0 because they're going to cancel each other out up and down here. I'm going to define this as positive. So yeah, so now I need to find what the x component is. Well, the x component is just the cos. So if I can define this as theta, cosine. And this is the same theta, right? Theta. Then this is going to be cosine theta is, cosine theta is the x adjacent over hypotenuse. So the x component over the hypotenuse, right? So the x component, how do I call it? G1x. The magnitude of G1x is G1 cos theta, which is true as well for G2x is G2 cos theta. So the x component that I'm going to get is the sum of these two, which is, I'm going to plug this in there and this in there. It's just going to be Gm cos theta over r squared plus a squared, and it's just that added again. So it's just 2 times that. I had. And that's the vector. Yep, looks right to me.
Wait, yo, I have a question.
Yeah.
It's like about vectors, but wait, are you supposed to keep the I-hat if you already included the angle, or am I tripping?
No, you need to include the I-hat because this is in the x direction, right? This is in the x direction. So we could have done sine theta, and that wouldn't mean the x direction. If I did sine theta, then that would have to go in j-hat.
Wouldn't it be minus I-hat? Or are you taking that to your x direction?
This is my this is my positive x direction.
Oh, okay.
Yeah. Alright, bet, thank you.
Right? Okay, no problem. So does this make sense? And is this right? Did someone else try this? Looks right to me. I don't know. Then the next part of the question is, explain physically why the field should approach 0. So the gravitational field should approach 0 as r goes to 0. Wait, why should...
Oh yeah, because as
Because
r
they oppose each
decreases,
other.
the x component between the two decreases too. So before eventually when r
Oh.
becomes 0, you're gonna have m1 directly above point P and m2 directly below point P. And since they're both the same mass, it's gonna cancel out.
Yeah, the net field, should go to 0 as r goes to 0. Yeah, that's right.
Wait, can you explain that again? Whoever just said that.
Yeah, well, I mean, I can say quickly. As this point goes to this place here, right? So as r goes to 0, this is our r variable, which is this length. As that goes to 0, what are the forces acting on it? There's no more x direction force. There's only two exactly counteracting x and y direction forces, and so the net force is 0.
Well, alright, thank you.
Yeah. No problem.
Oh shit. Yeah.
Right, and so that's why that's kind of half mathematical, half physical. But yeah, so as r goes to 0, then what happens here? We get cosine. Well, theta becomes 90, right? Theta becomes 90, and then cosine of 90 is 0, right? Hold on, let's check that. Cosine, goes like that, and then that would be pi, and so pi over 2. Yeah, okay, yes, cosine of 90 is 0. So this would go to 0. Obviously, this value here would be 0, but then also this angle would turn into 90 degrees. So cosine of 90 is 0. That's what I'm saying. That's for part C. Explain physically why the magnitude of the electric field of the not electric field, but the gravitational field should approach that value as r goes to infinity. So as r goes to infinity, let's see. As r goes to infinity, theta goes to 0. So cosine of, so I should say for part D here. As r goes to infinity, so we have 2gm over cosine of 0, right? 2gm, g and m are not, well, 2 is not affected, g is not affected, and m is not affected by distance, right? So cosine of 0 is 1, so the cosine leaves from the top, right? And in the denominator, you just get r squared plus, well, we're not supposed to get a squared, so for now let's just write that. But we get r squared plus a squared. A is not affected, right? A doesn't change here. How this
Did we
is.
just ignore a because
yeah,
r is so much greater than a?
Yes, exactly. You essentially just ignore a. Like imagine you pull this point way over here. This distance becomes less and less important the further you pull it out, and so now that it's infinite away, it's like r goes to infinity, those become completely negligible, and so a doesn't matter, and you just get that.
Can I say what I think?
Yes.
If we can use some calculus, can't we say anything divided by infinity, like r squared, infinity plus a number is infinity, and anything divided by infinity is 0? Can we say that?
You can You can say that the gravitational field goes to 0, right? The gravitational field goes to 0, but that wasn't really the question. The question was, as r goes to infinity, why is this expression what's describing the gravitational field? But you're right. Like as if I have 2gm over infinity squared, yeah, that's 0. Right? Or if I say r squared, the limit as r goes to infinity of that is 0. But again, that wasn't what the question was asking. The question was asking, why do we get this expression? Right? Why do we get this expression?
Oh, is it because the a becomes negligible?
Yeah, the a becomes negligible, exactly. Because again, imagine pulling that point P all the infinitely to the side. It doesn't really change much if they're a apart or if they're 0 apart. Right? If a is 0, it doesn't really change anything. So, yeah, a becomes negligible. And
so theta also goes to 0, right?
Theta goes to 0 because that angle is getting squeezed tighter and tighter, right? So theta and cosine of 0 is 1.
All right, thanks.
Right. So yeah. Okay, and that's the question. That's number 6. So number 7 is looks like a web assign one. So that's probably good. Any more questions for number 6 before I move on? Okay. Sounds good. A spacecraft in the shape of a long cylinder has length of 100 meters, and its mass with occupants is 1,000 kilograms. It has strayed too close to a black hole having mass 100 times that of the sun. The nose of the spacecraft points towards the black hole, and the distance between the nose and the center of the black hole is 10 kilometers. Determine the total force on the spacecraft. Let's just start there. Determine the total force on the spacecraft. Okay. So the force on the spacecraft will be by the black hole is described by this equation right here. So the magnitude of the force is that. So what we're looking for, Fg, the magnitude of Fg is, so capital G, M1, M2, so that's, well, it's just M1, M2 over R, well, okay, I'm kind of just writing everything again, but M1 is the 1,000 kilograms, that's the spaceship. M2 is 100 times the mass of the sun, which we'll have to look up, and that's everything we need. Oh, and R is, so we guess we just say determine the total force on the spacecraft, I guess just from the tip, so 1,000 kilograms.
Wait, isn't it, I'm pretty sure, isn't it like 110 kilometers and then 50 meters, because eventually the center?
Yeah, okay. Sure. I don't know if that'll get us the answer, but yeah. It doesn't really matter because it's 10 kilometers, but your number is going to be close enough if you choose any point on the spaceship here. But actually, no, since it's a black hole, then you might be different value, but we'll see. I need to find the mass of the sun, though. So mass of the sun. Spelled too many words.
1.989 to just the integral 30.
Thank you. So is it the same number that I'm about to read right here? 1.989 times 10 to the 30?
Yep. Yeah.
Okay, good. So that's the mass of the sun. So the second mass is 100 times that. Okay, so just plug this in, and I get 6.67 times 10 to the negative 11 times 1,000 times 100 times.
Yeah.
Well, someone's asking a question, but they are cutting out, so I cannot hear them, but hopefully they can ask in a second. 50. Okay, I got the force is 1.3135 times 10 to the 17 newtons. And let's take a look if that is, yeah, we have the answers for this one. So number 7. Number 7. 1.31. Yep, that's fine. That's good. Okay. So just use
I guess you were supposed to take the middle of the aircraft.
It rounds to only 2 decimal places, so I don't know. Like maybe it's like only a small difference there, so I don't know if that will be seen here, but yeah. Same answer. What is
Just a quick question.
Yeah.
I'm sorry. Yeah, no, go ahead.
No, I was gonna start doing B, so yeah, you go for it.
Oh no. On the test, they ask us to not write in the significant digits or the significant notation, right?
The scientific notation here, yeah.
Yeah, scientific notation. Sorry. How can we write this answer?
Oh well, you wouldn't get an answer like this in the test. If you had to, you would go 1 3 1 3 5 1 2 3 4 1 2 3. No.
And 17 zeros.
3 4. Well, and then 13 zeros because I already accounted for a couple places here. So 13 zeros after this. Right? And there. That's how you would write that. But you wouldn't get a question like that. They wouldn't give you a question where you have to, I mean, according to Springer from today, he said you won't get a question where you have to use scientific notation like that. It'll just be a whole number. Okay? Good? Okay.
Yeah.
Okay, sounds good.
Just quick question. Why did you add the 50 meters to the race? Why is it 10,050?
Just because halfway through the spaceship's 50 meters long, 100 meters long, so Halfway would be
Okay,
another 50
makes
meters. Yeah. Okay. Part B. What is the difference in the gravitational fields acting on the occupants in the nose of the ship and on those in the rear of the ship, farthest from the black hole? That would be the same. So I guess I have to do two calculations here. It's the same calculation, but I just have to set R equals 10,000. That gets me some answer. And R equals 10,100. That gets me some answer. So let's see what the answer is. So luckily my calculator saves it. So 10,000. So I get 1.3266 times 10 to the 17, and for the 10,100, I get 1.3005 times 10 to the 17. And the difference would be I don't want to type it all again. Okay, it's fine. I can just type it again. Minus 1.3266 times 10 to the 7. Oops, not answer. Times 10 to the 17. So the difference is... Whoa, that's... Cannot be right.
It's supposed to be a big number, yes. If you got like
It's supposed
3 to the 15.
It's supposed to be a big number.
I did get a big number. How is that a big number? Why is it to the 15?
Because it's a black hole, so the force exponentially increases. It's supposed to, if you read the next thing, it says like the difference in acceleration grows.
Oh, I see. Yeah.
Put the body of the ship under extreme tension.
Yeah. Okay. Yeah. I just kind of got confused about the decimal places. How it's working. Yeah. Okay. So it's fine. 2.6 times 10 to the 15 is what I got. Is the difference, and that's what the question was asking for. And yes. Oh, I got 10 to the. Why is it 10 to the 12? The answer says 2.6 times 10 to the 12.
I think you have an extra digit in the I got it as the same numbers but 10 to the 14. Same numbers but 10 to the 14.
Here, 10 to the 14 on both these?
Yeah.
For some reason, they didn't multiply by 1,000 or the mass of the ship.
So
Yeah.
They just
did
did,
it differently.
yeah.
Okay, so the book, yeah, I guess the book might have a wrong
Whatever,
answer.
we have the right. It's like
Wait,
it's
no,
a roundabout.
No, it's 10 to the power 12 because they're asking the gravitational field, not the force. So you don't need to multiply by the mass of the rocket.
Oh,
I see.
Okay, I was
He's
too
right,
quick
he's
to
right.
move on there. Yeah, what is the difference in the gravitational fields?
So it is 12 because
Yeah, it's 12.
So I just divide
By
by 10,000 here.
By 1,000. By 1,000.
By 1,000? Oh yeah.
Yeah, by
The,
1,000
the
because
mass
that's
the mass of the ship is yeah. Divide by 1,000 here, so that's 2.6 times 10 to the 12. Because the ship is 1,000 kilograms. Okay.
Wait, so why exactly? Like I didn't get. Why do you exactly have to divide by 1,000?
Because this quantity right here is the force, but the force is the mass times the gravitational field, right? We want the gravitational field, so we have to divide by the mass.
But like I thought that if we didn't use the mass of the ship in the calculation, then we're gonna get the field directly. No?
We did use the mass, and these are the forces.
Yeah,
this is the force that we got.
We could have just left the mass of the ship in the calculation in the first place.
Okay, that makes sense. Cause like that makes sense. Cause like I was a bit confused because I thought that if you didn't use the ship, why would you have to like divide by 1,000? But that makes sense.
But with the force, we did use the mass of the ship to calculate force. We did, right? But to calculate gravitational field, you don't have to. Just to correct it, we just divide by the mass here. Right. Okay. That's number 7. Number 15 is next. So I gotta find the question. Number 15 is here. This is on gravitational potential energy, so that's...
I have a question. I have a small question.
Yeah.
What would be the unit for it?
What would be the what, sorry?
The unit of...
The answer
the
here?
unit of the field, yeah. Acceleration?
It would be meters per second squared.
Okay, thank you.
Because remember, force is kilogram meters per second squared, and here we're dividing by kilograms, so it would be just meters per second squared, yeah. Okay, so for question 15, we assume this and we assume, that the gravitational potential energy is 0 at r equals infinity. So how much energy is required to move a 1,000 kilogram object from Earth's surface to an altitude twice the Earth's radius? So how much energy is required? Well, that sounds like a delta U thing. So delta UG is something, and I will find the something. Delta UG is this right here. So, what do we know? We know the mass of the object, which is one of the m's. We know the mass of, so m1 equals 1,000 kilograms. Mass 2 is the mass of the Earth, which I'll find out. Ri is the radius of the Earth, and Rf is twice the from the Earth's surface to an altitude twice the Earth's radius. Yeah, this was on the web assigned too. So we're going from here, which is Re, to an altitude that is twice the Earth's radius. So that's Re plus Re. So our actual new Rf is 3 Re. Does that make sense? It's just the tricky wording here. It's not 2 Re, it's 3 because it's the original radius, and then you're going to an altitude twice the Earth's radius, so 2 more Re's. And then we just need to find the mass of the Earth and the radius of the Earth, of course.
That's 5.972, 972 times 10 to the power 24.
10 to the power 24, that's the mass, right?
That's the mass, and I think the radius is... Oh, but that's... Never mind. No, it's not. Never mind.
The initial radius is, the altitude is the radius of Earth, which means it would be twice the radius of Earth.
Where? Where?
The center. Oh, from the Earth's surface. Never mind. That's a different question.
Okay. I just need the number for the Earth radius here. I'll look it up.
6378 kilometers. So.
63.
No, 6378.
6378 kilometers?
Yes. Yes.
That's the radius of the Earth? Okay, so then that many meters? Or 6.387 times 10 to the 6?
I posted the table with all those units in discussion.
Oh, good. Yes. Thank
It's
you.
just a screenshot from the textbook.
Oh, thank you. Yeah, that's good to have. I probably will put that in my notes, actually. I'll find it. Thank you. Oh, and just to make sure, we're good with people, like the amount of people in here, right? We don't need another streamer. I can't tell how many people are here, so I can't see the number.
You want me to close the stream?
No. I mean, I think like it's good that you're here. We don't need any more. I mean, like we don't need a third one. I just want to make sure. Thank you.
I don't think you ever reach 100 people like that. Have you ever?
We
reached
have.
100 people?
We have. Twice, I think.
Wow.
Yeah, the Zoom call was like 150 people.
At the start, yeah.
That was a special occasion.
Yeah. We have on the Discord server, I think, twice reached 100 people. So I just want to make sure. Usually the day before a physics test is when we reach 100 people. So that's why I was just checking here. But looks like we're good. Yeah, I'm going to use this formula now to find delta UG. So delta UG is, I'm just going to plug all that in, right? Delta UG is, so I'm just going to use this formula to calculate it. So let's plug it in. So it's a fraction minus a fraction. The first numerator is 6.67 times 10 to the negative 11 times m1, which is 1,000, times m2, which is 5.972 times 10 to the 24, over the initial radius, which is 6.378 times 10 to the 6. Okay, 6.67 times 10 to the negative 11 times 1,000 times, again, m2, which is 5.972 times 10 to the 24, over the final radius, which is 3 times the other radius. I guess I could have simplified a little bit there, but it doesn't really matter. 6.378 3 times 6.378 times 10 to the 6. Not times 6, sorry, times 10 to the 6. Okay, and I get that the delta U is 4.16 times 10 to the 10 joules. Let's see if that's right. Nope. Oh, yes, it is right. Never mind. I just can't count. Rounded differently, but probably some of these constants were rounded slightly differently. Yeah, they're good. Okay, so how is everybody feeling with that question? Okay, pretty good.
I will say easy.
That was nice. That was really easy. I don't think that's gonna be on.
It's just a word.
It's just one question, right? I mean, it's just one equation. I mean, right? It's just one.
Yeah.
One equation. So
you can actually vector out the G and M's and everything else, I guess.
How here with this one?
Yeah. So yeah, you just G M1 M2 times R initial minus R final. Like 1 over R initial.
Oh, factor this out. Yeah. Factor the GM1 M2 out. Yeah. You could do that, and that would be less typing into your calculator. Yeah. That's it. Okay, let's move on to 17. 17 and 19 are the last two chapter 13 questions, so we're doing good. A system consists of 3 particles, each with mass 5 grams, located at the corners of an equilateral triangle with sides that long. Calculate the gravitational potential energy of the system. Assume the particles are released simultaneously. Describe the subsequent motion of each. Will any collisions take place? Explain. Okay, it's kind of a tricky question, so let's take a look. So I'm going to draw it. We have, I'll draw it a little smaller. Equilateral triangle. Each mass has a mass m. M equals 0.005 kilograms. Okay, the distances here are all L, and L equals 0.3 meters. Yeah. Calculate the gravitational potential energy of the system. I'm quite certain that just means we find the gravitational potential energy of each pair and then add all the pairs together. I think that's what we do. So U total is the gravitational potential. I'll call this one 1, 2, 3. So the gravitational potential between 1 and 2 plus the gravitational potential between 2 and 3 plus the gravitational potential between 1 and 3. I think. Does anybody else think I'm doing the right thing?
Yeah, but since it's like they have all the same radius, can't you just make them equal to each other so it's just the 3 of one of them?
Probably.
Yeah, that's true.
Probably. There would be no difference between them at all.
Because they have all the same radius, right? And the same masses.
Yeah, it does. That does seem like it. So I'll call it 3 U pairs. I'll call it UP for U pairs. So U total is 3 times, well, each pair is going to have a gravitational potential energy of this. Sorry, I kind of took a bad screenshot there, but it's okay. So it's just going to be negative G M squared over, and now R is just L. Yeah. So U total is negative 3 G M squared over L. And that is going to be negative 3 times 6.67 times 10 to the negative 11 times something squared. That something is 0.005, I think. Yeah. Over L. And L is 0.3. So I got a total potential energy of negative 1.6675 times 10 to the negative 14 joules. So 17, let's just check that. 1.67 times 10 to the negative 14. Yep, that's good. So hopefully that's all good. Then B, yeah.
Oh, I was just gonna ask, so you know how you did U1 I mean, sorry, U and then for 1, 2. But then how come like you didn't do U and then for 2, 1?
For like these two?
Yeah, like the pairs, like you did 1, 2, right? But then what's the reason for not doing 2, 1 though?
Well, because this quantity is the amount of potential energy in the system of 1, 2. Right? So
Yeah.
right, so the system of 1, 2 and the system of 2, 1 are the same system. So it's the same potential energy. It's the same thing. So this variable is the same thing as if I said 2, 1.
Okay.
It's just saying object 2 and object 1, object 1 and object 2.
Oh, alright. Alright, thank you.
What's the potential energy that they share? It's the same if you look both ways.
Yeah. Alright, bet. Thank you.
Okay, no problem. So then part B is asking question? That's this. That's this. Right? Oh, I hear my own voice. R1 is 1000. So okay, we're good. Assume the particles are released simultaneously. Describe the subsequent motion of each. Will any collisions take place? What is the motion of each? Well, okay, we have a gravitational field this way, this way, this way, this way, this way, and this way, all equal. So are they all going to just collide right here? Because the net...
I think so.
The net force on all of them are like that, and it'll always be like that, even if they, come in at the same rate. Because if they're all here, then it's still the net force is still in. So yes, I think the answer is they collide at the center. I'm gonna check that, but the particles collide at the center of the triangle.
That makes sense. I don't know if that's the right answer, but that makes a lot of sense.
In my head, like that's how I'm picturing it.
And it is right. It is right. That's the answer. So yeah, the net force is to the middle. It'll always be to the middle, and they will just all collide in the middle, given no friction, no whatever. So yeah. Okay, so that's 17. We have one last question from chapter 13, which is number 19, right? Number 19, yeah. So number 19. Number 19 is this one. A 500 kilogram satellite is in circular orbit at an altitude of 500 kilometers above the Earth's surface. Because of air friction, the satellite eventually falls to the Earth's surface, where it hits the ground with a speed of 2 kilometers per second. How much energy was transformed into internal energy by means of air friction? Okay. So to do this question, you essentially have to remember, first of all, that if no energy was lost, delta K plus delta U would be 0. But energy was lost, which means some other force did work on the system, and so delta K plus delta U is equal to the non-conservative work. I think the negative non-conservative work. Because it doesn't really matter. We'll just get a absolutely different value. But
yeah, it's negative.
It is negative? Okay. So the non-conservative work is the amount of energy that was transformed into internal energy by means of something else that wasn't either the kinetic or the potential energy. Okay. So, well, we just need to find delta K and delta U. We know that... also, I see that 2 people put questions in the chat. We'll do that right after this. When I originally did this question... It was just, see this for a second. Yeah, I expanded all 4 terms here, but there is, I don't know if it's easier. I don't even know exactly what I'm doing here. Let me check this quick. The potential energy stored between pairs of objects, the total energy in a circular orbit. So there is this formula that we can use here, and that's the total energy in a circular orbit is that. I'm assuming that means potential energy. Maybe I just didn't write that in my note properly. I'm assuming that means the total potential.
No, it's the total kinetic plus potential energy.
Okay, so that means Ki and Ui are both that?
Together they're that, yeah.
Yeah, okay. So what I'm going to do is I'm going to say this is Kf minus Ki.
I don't know if we need that here. Because you can directly just substitute for the delta Q and...
Yeah, you can. I think it just simplifies a little bit. It simplifies a little bit here. Because what's going to happen is that Ki and Ui, but they're both negative. It's okay. because yeah, it's okay. So I can rearrange this to kf plus uf minus ki plus ui equals negative work non-conservative. Well, this is equal to ki plus ui. That is that. So this is just going to be kf plus uf plus gm m over 2r equals negative work non-conservative. So you don't actually have to do that. You can totally find what ki and ui are separately, but this just knocks off one whole fraction that we have to deal with, because now it's 3 fractions instead of 4.
Wait, how'd you get that?
This formula up here?
Like, how'd you convert the ki and ui into thing?
Positive or?
No, into gm m over 2r.
Because I have this formula.
Okay, but I mean, like, how come ki plus ui equals that though?
Why exactly? I think it's just if you like were to work it out, if you were to, so ki is the kinetic energy that it is up there, which is going to be 1/2. Yeah.
Is that just the thing? That
This,
ki plus
yeah. This is just this is a formula. This is a formula in my notes.
Okay, alright then, never mind.
We can spend a moment to derive it on the side here. I'll note here.
Oh no, it's okay. I just thought that it's like a whole thing that you just did or something.
No. That's just some from my notes. I have total energy in circular orbit is defined as, and then it's this.
Alright, bet. Thank you.
No problem. Although I would like to see how that. Maybe I'll try to derive it after, but when we're done, everything else is fine.
So we can't be using that equation that we have right there on the top right for the final position of the satellite. No. Right, because it does lose energy due to an external force.
Well, it crashes into the Earth's surface, so it's not orbiting anymore.
Yeah,
right?
So that means we can't be using that E total equation for the final position.
No, that's
okay.
Yeah. So kf is going to be 1/2 mvf squared. What are we looking for? We're looking for, we're just looking for work non-conservative. So we just have to find what all the left side is. So this is going to be plus uf. So uf is the final potential energy, which is going to be negative g m. So m is the Earth, and big M is the Earth, and little m is the satellite, over r plus g m over 2r equals negative work non-conservative. So we know everything. We know the final velocity, vf, equals 2,000 meters per second. We know the mass, which is a 5,000 kilogram thing. We know r equals, it was 500 kilometers, so 500,000 meters. We know the big mass. We don't know the big mass yet, but I'll find that. And little mass is 500 kilograms. And that's everything. We just need the big mass, which is the mass of the Earth, which is Earth 5.97 times 10 to the 24.
By the way, do you also do plus the radius of the Earth, or?
No. Hold on. Yeah. Yeah, you're right. Circular orbit at an altitude of 500 kilometers above the Earth's surface. So you're right. This is 5 kilometers plus the radius of the Earth, which is 6.37 times 10 to the 6 meters. Right. So that's going to be our R there. Yeah, you're right. And then now that's everything. So we just find this and take the negative of it, and that'll be our answer. So, first fraction. M, 500 times something.
Sorry, Adam, before you go ahead, aren't the two R's different? Like the R from the orbit is different from the R final?
Yep. You're right. This is Ri. Ri is that. Rf is just 6.37 times 10 to the 6 meters. This is RF. Does that make sense? The final radius is just the radius of the Earth. We land on the Earth. The initial radius is the radius of the Earth plus the altitude we were at before. So 500 times 2,000 squared over 2 minus the fraction 6.67 times 10 to the negative 11 times something. That something is 5.97 times 10 to the 24 times 500. Did I do 500 or 5,000 for the first one? 500, okay. And the denominator is RF, which is 6.37 times 10 to the 6. And our final fraction is plus 6.67 times 10 to the negative 11 times something, which is 5.97 times 10 to the 24 times 500 over 2 times Ri, and Ri is 500,000 plus 6.37 times 10 to the 6. So I got that the work non-conservative is 1.5765 times 10 to the 10 joules. And let's see if that's right. 1.58 times 10 to the 10 joules. Yep, we are good. So that is the non-conservative work. And that is how much energy was lost due to air friction. And we're done chapter 13. Any questions?
Yeah, so with the values that we are given initially in the question, would we be able to find the velocity initially of the satellite as it was orbiting?
The initial velocity? Probably. Yeah. Let's see.
Because like I tried it like the traditional way of like actually finding KF, knowing what KI is, finding UF, and finding UI.
Well, to do that, to do KI, you need VI squared, right?
Yeah, exactly. And I want to know, how would we find VI squared?
Well, I think you would use the fact that when you're in a circular orbit, this is true. This is true. And so V would be the square root of that. But since you're looking for V squared anyways, it would just be G
Sorry,
times...
your head is kind of covering. You just slide it over
this one here?
a bit to the left.
This one here.
Yeah, there we go.
Right?
Okay.
That,
so the mass of the satellite. Okay.
That's the that would be initial velocity if you wanted an initial velocity there.
I see. Okay. Right. Sounds good.
Also, about that, I'm pretty sure this is the exact same thing as what you just said over there. This is probably the reason what I'm about to say is true, but KEI, right, the initial kinetic energy, is equal to -1/2 of the potential energy, you know?
Of the initial potential energy?
Yeah.
Yes, yes.
Alright, bad.
It's in the notes.
Yeah, and it's probably because of what you said.
Again, what did you just say?
Yeah, well.
That's technically just the half. Actually, the formula that you have for the velocity, you just divide that by 2, and that's the half of the half of the potential energy, the one that you showed us before, the V squared one.
Oh, this formula here.
Get it? Yeah, you just divide this by 2 and multiply it by the mass, and here you go. It is the potential energy just be divided by 2.
Yeah. But then if you... Sorry,
go ahead.
I was going to say, if you multiply by mass, you divide it by 2... Oh, yeah. Yeah. You get this formula, pretty much. You get this. These two formulas are not... well, I don't know why the negative sign's there, but...
Yeah, there's gonna be a negative sign when you do it.
It's also not squared. And why is the kinetic energy equal to that, but not the potential? Okay, I don't even know what I'm pondering now. So, what's the question? Yeah, what's the?
Sorry, I just got a question about that velocity equation that you have there. Velocity squared equals GMS over R. I think I said that would be the mass of the satellite, but that's not true, right? It would be mass of...
No, that would be the mass of the source. Is what S is mass of the source.
Sorry. Yeah.
Okay. Are we good to move on? Good to move on to chat question. I have a chat question for waves here.
Wait, what's the final answer that you got?
1.58 times 10 to the 10.
Oh, okay.
Which is right.
Okay, nice.
Okay. Good to start question 6 from this this chat question I got. Okay. So consider the apparatus shown in figure A below, where the hanging object has mass m and the string is vibrating in its second harmonic. The vibrating blade at the left maintains a constant frequency. The wind begins to blow to the right, applying a constant horizontal force F on the hanging object. What is the magnitude of the force the wind must apply to the hanging object so that the string vibrates in its first harmonic, as shown in the figure below? Use any symbol. Okay. What?
Adam, you're echoing for me at least.
Did you mute? Is it from my stream, or is it because you hear both streams at the same time?
Like, I don't know.
Am I echoing from everybody else?
No, you're fine.
Yeah, a
here.
little bit slow.
You have to mute the stream audio if you're watching the other stream.
Yeah, if you're watching two streams, like there's the other stream, that there's like the two live streams. So if you want to mute the other one so you don't hear me.
Okay, guys, thank you.
That would be the other one. Okay. So, this is a good question. So we need to find what is the magnitude of the force the wind must apply to the hanging object so that the string vibrates in its first harmonic as shown below. Okay, what do we know right now? Right now we know that it's in its second harmonic. So F2, right? F2 equals 2V over 2L. Right? Or which is V over L. Which is V over L, right? Well, we know that. That's what we know. We want it to be in the first harmonic, which is going to be V over 2L. Right? So I want to know how much stronger the other tension is, because remember, this is just a tension. This is tension over mu. Tension over mu. I want to know, and also something to note here, F1 equals F2. Now, I want to know how much stronger that second tension has to be for, this is for the, I don't want to confuse the writing, so I'm going to call it T2, but T1 is our, this is our, T2 is the one with the second harmonic, T1 is the one with the first harmonic. So we want to know how much stronger the tension is in the first harmonic than the second harmonic. So we want to know T1 over T2. Because from that, we can figure out the force that needs to be applied with this string like this. What's that force of tension? And then we can figure it out from there.
And then also, what you can do is you could just set F2 and F1 equal to each other. So
Yeah.
you wouldn't have to find the ratio as well. Okay.
Yeah.
Yeah, so there are two ways.
Right. There's like right there like that. Right? So I'm going to do now, well, I'm going to rearrange for, what would I Yeah, I'll just rearrange for T1 in both these cases, or just the T. So it's going to be L.
Isn't it?
Yeah.
Sorry, isn't it T2 over T1?
No, because I want to know the tension in the first harmonic compared to the tension in the second harmonic. This is the initial. My writing is a little hard. The notation that I'm using is a little difficult. So initial, and this is the final. Because we're going from the second harmonic to the first harmonic.
But the question is asking for the force applied to make it this.
So I need to know what the tension is supposed to be in the second, when we're in the first harmonic. So this.
Yeah. One refers to the first harmonic.
Second harmonic. This is the first. This is the first harmonic.
Oh, sorry. I thought.
Don't worry.
One and that's.
Yeah, I know. Don't worry. So T2 over mu, and so then just times mu equals T2. And then this is going to be L squared F2 F1 mu squared as well equals T1. So T1 over T2 is going to be L squared F1 squared mu over, this isn't going to look good, L squared.
No, yeah, things would cancel out now, right?
There's supposed to be a 2 here. There's supposed to be a 2 there. Yeah, there's supposed to be a 2 there. There's a 2 here. Okay. Then
It's
we
supposed
just...
to be
Would that 2 be squared?
no. Yeah, it'd be 4.
It'd be 4. Yeah, you're right. 4. L squared F2 squared mu. So everything cancels here except the 4. So what we know is that T1 is 4 times as big as T2, right? So I just need to find what the tension is here and multiply that by 4, and that's the tension that needs to be here. So I'll quickly do a free body diagram. So this is when we're in the first harmonic, or no, sorry, we're in the first situation, but second harmonic. So all we know is that there's nothing happening here. It's just that the force of tension, we'll call it big T. So T2 equals mg, right? Mg, big M for that. Now in the second situation, which is called when we have the tension 1, tension for the first harmonic, we have 2 forces happening here. We have the applied force, Fa, which is what we're solving for, right? What is the magnitude of the force? Yep. The applied force. We have this force of tension going up here. So I should really just draw it from there. Force of tension. And we have a force of gravity pulling down. So the applied force is only in the x direction, which is convenient. So I need to...
You can take the x and y components of the tension force.
Yeah.
And equate them.
We don't know what angle that is, but we'll just have to say it's theta.
No, you wouldn't need the angle. So when you equate the components, so the x component will be equal to the Fa, and the y component would be equal to the Fg.
Oh, okay. So force of tension. Oh, I guess so. Okay, force of tension y is equal to force of gravity. Force of tension x is equal to the applied force.
Exactly. And now you find the net. You find Ft by root of Fty squared plus Ftx squared.
Oh,
like,
I find
just finding the magnitude,
Ft by the square root of f. Yeah.
Fty squared.
F. Yeah. Okay. Yeah. F. So I should call this. This is T1. T with the first harmonic is F.
Sorry, guys.
Yeah.
Can we say that T equals Fa over cos theta?
I want to kind of avoid thetas here. I want to avoid thetas because we don't know what angle, and yeah, I could use thetas. But this works too. So T1 is, well, that's T1. So then I have to change this to the square root of... Use any variable symbol given in the problem as well. Okay. Then I have to change this to F force of gravity squared plus the applied force squared. Okay, doing another step here. And then finally we have that this is mass big M squared times G squared plus the applied force squared. That's T1. We also know that T1 equals 4T2. So I can say that 4T2 equals the square root of big M squared G squared plus FA squared A. And finally, we know that T2 is mg. So we know that M4 mg equals the square root of m squared g squared plus f squared a. Oops, plus f squared a. And we just rearrange for f squared a. So 16 m squared g squared equals m squared g squared plus f squared a. So 15 m squared g squared in a square root equals f squared, fa. So root 15, which is 3 times 5, which isn't anything, or yeah, okay, don't think I can simplify that. Root 15 mg equals the force applied. And there's that.
I got a kind of a different answer.
Yeah, maybe I made a mistake. I don't know. Let's see.
No, I think that is
I use completely different method.
Did you get the same answer or no?
No, I got F equal 4 the tension of the second harmonic times the tension of the first harmonic in the X over the tension of the first harmonic.
Okay, you have to simplify those things though. You can simplify because the tension in the the tension in the second harmonic is mg. Right? Tension in the second harmonic is mg. Tension in the first harmonic, well, we just showed it here. The tension in the first harmonic is the square root of m squared g squared plus fa squared, the applied force squared. So you can plug that all in and see if you can simplify and solve.
Oh. I see. So he wants it in terms
mass. I didn't quite get the mass.
Hold on, mass. 1 second. He wants it in. Just in terms of m and g, capital M and g, and the applied force is what we're looking for. He wants it just in terms of mg, because it says use any variables or symbols given in the problem as well as g. Well, we're only given m and f and g.
Oh, okay.
And sorry, was there another question about mass there, or are we good?
Sorry, I thought they gave us mass, right?
No, they didn't give.
Like,
It's all variables.
It's all variables.
It's
just variables. Yeah, I know.
I don't know if this is right, but this is my answer. I don't know.
I maybe I'm remembering it wrong here. Let me pull it up. I thought the answer was root 15 mg, all under the square root, but let's see.
Yeah, that's the answer.
What I did is right?
Yeah.
Okay.
Okay,
Good.
you're good. Yeah.
Good. We're good. Thank God. So yeah.
Yeah. After I simplified, I get the same answer.
Okay, good.
Sorry.
Good. No, don't worry. Yeah, good. I'm happy you got the right answer. So I'm happy to stop and explain this question. Why did it send me to the top? I'm scared that if I move a picture around, it like moves all the text. And anyways, I'm happy to stop and explain this question if someone wants me to explain it more, because there was a lot of algebra here.
Just re-explain just for everyone, I guess.
It's what? Sorry?
Just re-explain it for everyone.
Go through it? Okay, I'll draw steps here. I like drawing steps in yellow for some reason. So, the first step that I did was really this. What am I trying to find? I'm trying to find the ratio of the tensions. Because when I find the ratio, like what connects the wave part to the force part is that force of tension, right? So since that force of tension is connecting them, what if I just find how much bigger the tension is here compared to how much the tension is here? That'll help me find what I'm looking for with the forces after. I can forget about the force going on there for now. So that's my target for now. Target 1. So how will I find that? Well, I know that in the first situation, this is true. The nth harmonic is nv over 2l, so just simplify a little bit. There's 2 2's here that canceled. And this is v. And similarly, in the first harmonic, right, so this is my second step, is I have this. So this is using the Fn formula. Then what I do is I rearrange, in step 3 here, I rearrange for T1 over T2. And remember, T1 is not T in the first situation. T1 means T with the first harmonic, right? So the first harmonic is the second situation, and the second harmonic is the first situation. It's like a little weird how I have to say it, but I don't really know a better way to say it. So hopefully that makes sense. So T1 is with the first harmonic. T2 is with the second harmonic. So I rearrange both for T1 and T2 separately, and then I take the ratio. So I get that T1 is 4 times as big as T2. Okay. So I get this equation right here. Okay, so then step 4, step 4 is find this equation. Step 5, so just T2 is mg for the first situation. This is T, this is T2, this is mg. Okay, step 5 is now find an expression. Find an expression for T, this should be T1, for T1, right? And I did that. I found an expression for T1. And notably, it has to containing FA, the applied force that we're looking for. Because when I do that, I can find this expression for T1, which is actually which is actually this down here, right? I can then plug in the fact that we know that T1 is 4T2. So I get 4T2 over here. Let me just put that here, 4T2. And then I can use the fact that we know that T2 is mg. And finally, I can just have an expression that's fully just in terms of mg and the applied force, and I can just rearrange. So step 6 is rearrange for FA. FA. Whatever. And that's the final answer. So does that make sense?
Yep, totally.
Yes, it does.
Okay, good. Happy to hear. Let's
I
take a
don't
look.
think
Yeah?
question like this will be like a multiple choice.
No, but I definitely think tomorrow's test has a ratio because there's so many of these problems you have to take a ratio. So you will probably have to take a ratio like this. And a part of this would be a part of the multiple choice, right? Not the whole thing, yeah. Okay, let's try this question. This potentially is the last question for today because it is 9:40. So let me just see. 1 second. Okay. Oops. Sorry. So the object shown orbits. This is our next question, which apparently is from Springer's lecture, I guess. The object shown orbits Earth. The object shown orbits Earth. Oh, that's the object there, I guess. Point A is 1,000 kilometers from Earth's center. Point B is 200,000 kilometers from Earth's center. If the potential energy at A is that, what is the total energy of the orbit? Well, the total energy of the orbit is the formula that we used over there. So let's see. The total energy of the orbit is this. The potential energy, we know that the potential energy at A, I also need this formula, is that. So at A, so U, the potential energy that we know, U equals -3 times 10 to the 6 joules. So we know that U equals -g m. M is the mass of the Earth. M is the mass of the object. Right? Over 2r, call it R1. R1 is 100,000 kilometers, so 100,000 kilometers, so 100 million meters. Yeah. So we know that that's true for these specific numbers. We're looking for the total energy. What is the total energy of the orbit? So
well, you can't use the U formula to find the mass of the object, and then just use.
Yeah.
You have to find the mass of the object, and after you find the mass of the object, you can just like do the E formula and find the total energy.
I realize. Yeah, I think that. Let me just quickly say this. Yeah, I think you're onto something there. We actually have to use this formula because it's not a circular orbit. This is for circular. This is for elliptical.
Well, I mean, the way you were going about it, you had R1, and then you would have done the exact same thing with R2. And we knew that the R1 and R2 would equal 2 times the radius of
the long axis.
Yeah.
Right?
So
which is this.
Eventually you would have gone there. Yeah.
Yeah, that's right. So just to be clear here, A is the long axis. So 2A is that total distance. 2A is R1 plus R2. R2 is 200 million meters because it gives us that in the question. Okay, So I need the total energy. Well, I have 2a. That's fine. I have the denominator. I have g. I don't have the big mass. Although I can just find the mass of the Earth. It says it's the Earth, so maybe I can just find that. But I don't have the little mass. I guess I can find the little mass here. Yeah, I can make an expression for the little mass like this. So it's going to be 2... Oh, no. No. This is the formula I need. Where did I lose this? Negative... Why is there a 2 here?
Sorry, I don't mean to interrupt, but wouldn't you just use the regular, potential energy formula for point A to find the little m, and then obviously from that you can plug it into the elliptical E is equal to negative g mm over 2a.
Yeah, that's what I'm going to do. I just realized I wrote this formula wrong. I don't know why there's a 2 over here.
Excuse me. I have an idea too. Sorry.
Sure.
Can you just divide it by 4? Would you divide what we have by 4?
Why?
If the radius is increasing by 2, it's 1 over r squared. So the whole thing will be divided by 4.
I just use a regular potential energy, like circular for so A, and then just use the E, the E one. I'm so confused. I don't know.
This is the regular potential energy you're talking about, right? This one.
Yes.
Yeah, right here. What's the divide by 4? What is that?
Is 750,000.
What I remember Springer doing is...
It is points. Go. Right there.
Sorry, go ahead.
Do we have the answer?
Yeah, what am I dividing by 4, though? Sorry, what am I dividing by 4? This number?
The initial energy at A. Energy at A.
Yeah.
We're dividing it by 4 because the radius is increasing by 2. So you divided the whole thing by 4 because it's 1 over r squared.
The radius is increasing by 2? Okay.
So
energy does
it's
not
1
have a
over...
squared radius. Energy has a linear radius.
Oh,
the radius
so we divided by 2. Oh yeah.
Oh, whoever sent this, do they have the answer? Are they still here?
Yeah, let me check.
Okay.
Springer's lecture.
This is what I think.
Wait, what the Minatonomikaze? He sent the question.
Okay, I'm just gonna do this because I think this is right, and let's see where it gets us. Gm over 2 over r1 plus r2. Do I know everything in here? Yeah, pretty much. I mean, the m's cancel, and the g's the g's cancel. So the total energy is just r1u over r1 plus r2, which is r1 is 100 million times -3 times 10 to the 6 over 100 million plus, well, just 300 million. 300, 1, 2, 3, 1, 2, 3 million. So I get -1. I get C. -1 times 10 to the 6 joules.
I see what we were wrong. I'm sorry. I know what I'm wrong now.
Yeah? Okay.
He wants the total energy. He doesn't want the potential energy. He give you the initial potential energy.
Get what you did.
Yeah.
Oh,
yeah.
I see what I'm wrong.
Yeah.
I'm sorry.
Okay, don't worry. Don't be sorry. Yeah. You're all good. Is this the answer? Does someone have the answer?
Yeah, I think Minatonomikaze. He has the answer.
And what is it?
No, it is the answer. Yeah, I have the answer from the notes.
Okay, good. So, yeah.
Yeah, could you just clarify how you subbed in that -r1u?
Yeah, let me clean this up a little bit here. Okay. So, first step that I did was use the fact that they told us the potential energy. So I knew that the potential energy U at a certain radius R1 was equal to this. I then did step 2, which was rearrange for M. right? Because I know I'm using this equation here to solve for E. E total is the total energy of the orbit, of an elliptical orbit, right? Of an elliptical orbit. So this is part 3.
What?
Is this G, capital M over 2A. Someone's got their mic on. Someone's got their mic on. They're talking. Let's see who it is. Toasty 2478. Toasty 2478. You got your mic on.
Yo, Toasty, buddy boy. Your server muted now. Cool,
Okay, good. Thank you, Manuel. So this from the step here, we're looking for this. This is what the question is asking for. E total of an elliptical orbit. So what do I know? 2A I know. 2A is 2 times the long axis. That's this distance, which is just the distance between A and B, right? So that's just, well, it gives us here even, right? It's just RA plus RB. It's R1 plus R2, which is what I called it. So I have that here. So that's the denominator. The numerator, I know G, I don't know M, and I can find lowercase m, right? I can find lowercase m here. Or I could also have just found capital M. Either way, I rearranged this equation for that, sub it in, bunch of stuff cancels, denominator. These are all numbers I know. U is the potential energy that they told us.
Oh, so sorry, going back up. Okay, so right there, so you have the negative R1U over GM equal to M. You got that equation from rearranging the potential UG equals negative GM1 M2 over R.
Yeah.
By rearranging that.
Yep.
I see.
Wait, so the energy that they gave us is the elliptical energy, right?
It's the potential energy at one single point. At this one point right here. It's the potential energy right there. We're looking for the elliptical energy. Like the energy of the whole elliptical orbit.
Oh, so it's the original equation that we have to use, right?
It's
the normal UG that they gave us, right?
They gave us this, yeah. They gave us the information for this equation.
Alright, thank you.
No problem. Okay, yeah, guys, that's the. Oh well, there we go. There's that. Hold on, I gotta respond 1 second.
Oh, it's Kate
Yeah.
calling, huh?
Oh, she's here. Okay. Well, good timing, because that is it for today. That's the last question for today, because that's the last chat question I got to. But yeah.
Yo, you're kind of a physics demon. I read it.
Yeah. All right. Thank you. Yeah.